Hello guys, this is Himanshu from Code Campaign and we are continuing with our binary tree module. So today we are going to discuss about the top view of the binary tree problem. So before watching this video, I will highly recommend you go back and watch the vertical order traversal video because this video is completely or heavily based upon the vertical order traversal. So if you go back and watch that video and then come back, so you will be able to understand this video better. Okay, so now let's proceed. So what does this top view suggest? So the top view problem says if you are watching a binary tree from the top, right? If you're watching a binary tree from the top, so you have to print the view of the binary tree, okay, from left to right. Okay, so let's see. So suppose this is the given binary tree. So what will be the top view of this binary tree? The top from left to right, the top view will be, let's, so if we are seeing from here, we will be able to see only 4, right? So just imagine that you are seeing from this side, okay, and so you will be able to see 4, then you will be able to see 2, then you will be able to see 1, then you will be able to see 3, and you will be able to see 7. So you will not be able to see these nodes, right? As these nodes are hidden by these nodes because you're seeing from the top, right? So this will be our output. Okay, so let's take some other example to understand it better. Okay, so let's take this example. So what will be the top view here? So we are watching from here, from the top, right? So let's see. So we'll see 4, we'll see 2, we'll see 1, see 3, we'll see 7, we'll see 9, and we'll see 12, right? To understand it better, let's draw some vertical lines here. So this is our first vertical line. We'll say it L1. This is our second vertical line. We'll say L2. This is our third vertical line. We'll say L3. Right. This is our fourth vertical line. We will say L4. This is our fifth vertical line. L5. Right. And this is our sixth vertical line, L7. So actually 12 will not come into the output. So if you see here, all these vertical line. So on L1, how many nodes are mapped? 4 is mapped. On L2, 2 is mapped. On L3, 1, 5, and 6 are mapped. So 1, 5, and 6 are mapped. On L4, 3, 8, and 10 are mapped. 3, 8, and 10 are mapped. On L5, 7 and 11 are mapped. 7 and sorry 7 and 11 are mapped, and on L6 9 and 12, right? So to print the top view, what we have to do now, whatever node, if you see, we have written according to the order, according to the level of the node, right? So let me change the pointer here. Okay, so the level for this node will be 0, level for this node will be 1, level for this node will be 2, level for all these nodes will be 3, 11 for this node will be 4, and level for this node will be 5, right? If so here if you see 1, 5 and 6, they all are falling on the same line, but we are printing it according to the level. So uh, so the node 1 is on the 0th level, so we'll print it first, and then 5 and 6, they're both on the same level, so we'll print them from left to right, so 5 and 6. Okay, so now if you want to print the top view out of it, so this will be your top view, right? So what we have to do, if the more than one elements are falling on the same line, we have to just take the element which is on the higher level, right? We have to just take the first element which is on the higher level. If you're not understanding that, I will again say just go back and watch the vertical order traversal video, and then come back here. You'll be able to understand, because in the vertical order traversal video, we have to print this whole output, right? So I already discussed the complete problem there. In the top view, what we have to do, we are only concerned about the nodes which are on the top of the particular line. So here if you see, the 9 is on the top of this line, 7 is on the top of L5 line, 3 is on the top of L4 line, L3 is on the 1 is on the top of L3 line, L2 has only 1, so 2 will be on the top, and L1 also has 4 only. So this will be our top view, right? So okay, now let's proceed further and see how we can uh, go ahead and implement this problem. Okay, so let's take this example. So what will be the top view for this? Top view will be again 4, comma 2, comma 1, comma 3, and comma 7, right? So if you have watched the vertical order traversal video, so you already know uh, to to print the vertical order traversal of this particular binary tree, what we need to use one queue, and then we need to use one sorted dictionary, so which will have the key as the distance from the root node, and the values of the dictionary will be list of nodes, right? So this is for vertical order traversal, but in this case we only need to store one single node, right? We don't need to print all the nodes which are on a particular level, right? We only need to consider nodes which are on the top of that particular level. So as an example, here it has only one element, so it will be 4 will be considered, and then again it has only one element, so 2 will be considered. But here we have three elements, 1, 5 and 6, so only one will be considered because this element is on the higher level, right? And if you see it logically, if you see it from the top view, you will only be able to see one only. You will not be able to see 5 and 6. Then again in this same case of 3 and 8, we will only consider 3, right? So instead of taking this the list of value, we need to only take value as tree node. We don't need to store multiple nodes, we only need one node, right? So this is the only difference that is there in between the previous problem, the vertical order traversal, and this problem. So, and everything will remain same. So now let's go ahead and see how we can implement it by using the queue and the sorted dictionary. Okay, so so as we already know, for the root node we consider the distance as 0. For calculating the left node distance, we take the root node distance and add -1 to it, so this will become -1. And for this we'll take the, for calculating the right distance of the right child, we take the root node uh, we take the root node distance or the parent distance and add 1 to it, so this will become +1. Likewise for 4, we'll take the parent node distance, which is -1, and add -1 to it, so this will -2, and this will become 0. For this will again become 0 because we'll subtract -1 from here, and this will be +2. For this guy, this will become +1, right? So okay, so these are all the distances from the root node. Okay, so what we have to do here, we'll start from here and we'll take the node, which is 1, and we'll put its distance as well into the queue. Okay, then what we'll do, we will store we will then what we'll do, we'll first take the element out from the front of the queue, which is 1, and then we'll put it into the map. So first we'll check if the distance 0 exists into the map or not. So initially our map is empty, so nothing is there, so we'll add it here. That is the key will be the distance and the value will be the node. After this, what we'll do, we'll push its left and the right child into the queue. So the left child is 2 and its distance is -1, and the right child is 3 and its distance is +1. Okay, now again we'll pop the element from the front of the queue and then again check if the distance exists into the map or not. So distance doesn't exist, so we'll add -1 and 2 into the map. Okay, after this we'll push their child into the queue, so we'll push 4 and its distance and 5 and its distance into the queue. We'll pop again the front of the queue, so which is 3, and then we'll check if +1 key exists into the map or not. It doesn't exist, so we'll enter both of these. Now again we will enter the left and the right child into the queue, so this will be 6 and its distance is 0, and 7 and its distance is +2. Again we'll pop the element from the front of the queue and we'll check if -2 exists here, and it doesn't exist, so we'll put -2 here and we'll put 4 here. Okay, now we'll check if the left or the right child exists. For 4, it doesn't exist, so we cannot put anything here. Then we'll again pop the front element from the front of the queue, which is 5. Now again we'll check if the 0 key exists here or not. So it's already exists, so we'll not insert anything into the map. We'll just ignore this node. Then we'll again check if the left child or the right child for the node exists or not. So it doesn't exist, so we'll leave it. Then we will again pop out the element from the front of the queue, which is 6. Again its distance is 0. We'll check if the 0 exists into the map or not. 0 already there, so we'll not do anything. So we will check its left child, which is null. So we'll check its right child. So right child exists, so we'll put it into the queue, which is 8, and the distance is +1. Then we'll again pop the element from the front of the queue, which is 7. We'll check if +2 exists into the map or not. So +2 key doesn't exist, so we'll put 7 here. After this we will check if 7 has any child that we can push into the queue. 7 do not have any child, so we'll leave 7. Then we'll pop the another element from the queue, which is 8, and then we'll check if +1 exists into the map or not. So +1 key exists, so we will ignore it. Then we'll check if 8 has any child that we can push into the queue. So 8 do not have any child that we can push into the queue. After this, our queue is empty. So what we'll do, we'll go ahead and print our map, and as this is the sorted map, so this will give us the key in the sorted order. So first, so when we'll iterate through this map, first we'll get 2 and the value of the 2 is 4. Then what we'll get -1, and the value of -1 is 2. Then we'll get 0, value of 0 is 1. Then we'll get +1, value of +1 is 3, and then we'll get +2, the value of +2 is 7, right? So right, so if you compare it with the output written here, both are same, right? So that's how we can print the top view of the tree. So now let's go ahead and write the code for it. Okay, so this is where we left our ID in the previous video. So we wrote the vertical order traversal. So today we are going to write the top view of the binary tree. So as if you have watched the video of the vertical order traversal, then you already know that vertical order traversal and this top view of the binary tree, both solutions are pretty similar. So what I'll do, rather than writing the code, I'll just copy the previous code. And if you haven't watched the video of the vertical order traversal, I would say just pause the video here and then go back and watch the video for the vertical order traversal and then come back to this video. So I'll just copy paste this code here and I will make few changes to this code. So first of all, we need to change the function name. This will be top view of binary tree. Okay. And then what changes we have to do? Let's go back. So in the vertical order traversal, if you see here, we were using the sorted dictionary where we were storing the list of the node. But here, in this case, in the top view, we need to only store one node. So let's change this. So we need to only store one node. So we don't need list here. So let's change it into a node, tree node, and make the same change here. Okay. So that's fine. After this, what we have to do? Uh, we have to check into the map if the key. So what we have to do, let's go back here. What we were doing, we were getting the elements out of the queue and then checking if that key is already existing into the map. If the key is already existing into the map, we were not inserting the node into the map. And if the key doesn't exist into the map, we were inserting uh, the value into the map. So let's implement that here. So we have our this map here. First, we need to check if this contains the key. And so yeah, so let's check if this contains the key, and if so, what we have to do, if this contains the key, we don't need to do anything. If it doesn't contain the key, what we have to do, we have to insert the key and the value into the map, right? So let's insert to the map. Okay, so this is the thing. Then after this, what we have to do, like everything else will remain same, right? The everything, like here we are inserting the left node and here we are inserting the right node, so everything else will remain same. Then we have to change the print part here. So rather than getting the list of the tree nodes, we will get only one node out of here, right? So let's remove this for loop, and what we have to do, we have to just print the node that we are getting out of the tree. So the node, let's get the node out of the dictionary and then just print the data of the node. So that's all we have to do here. Okay, so now let's go back and call this function and check if this function actually works or not. So again, we have to use our traversal util and call our method. Okay, So now let's run this. Okay, so this is our output. Let's go back to our and compare it with the output. So yeah, let's compare our 4 2 4 4 2 2 1 1 3 3 7 7. So yeah, so it works. So our code works. Uh, in the last video, I forgot to tell the time complexity and the space complexity of this algorithm. So now let's analyze the time complexity and the space complexity of this algorithm. So the space complexity is pretty simple. As you can see, we are using the queue here, and in the queue at a particular so in the worst case scenario, in the queue, what we have to do, we will have to store all the elements into the queue. So the space complexity will be the number of elements into the queue. Now let's understand the time complexity of the algorithm. So to understand the time complexity of the algorithm, we have to understand what we are doing here. So we are taking each and every element and then we are inserting into the map, right? So for all the elements which are into the tree, we are doing operations on the map. So so what we have to do here now, let's come back here and just understand what is the time complexity for add or contains key operation into the sorted dictionary, right? So if you can see here, the sorted dictionary, if we want to add element, it takes log n, and if we want to check if the key exists, it takes log n. And these operations we are going to do on the n nodes of the n number of nodes of the uh, number of nodes of the binary tree, right? So the time complexity will be n nodes into and for n nodes, we are going to do the operation on the map, and one operation takes log n time, right? So one operation take log n time, and how many operations we have to do, equal to the number of nodes into the binary tree. So this will be our time complexity. So we'll say O n log n, right? So space complexity is O n, and the time complexity is n log n. That's conclude our video for the top view of the tree. So if you haven't subscribed to my channel, please go ahead and subscribe to my channel, and if you like the video, please press the like button. If you have any query or comment, please put it into the comment box. uh, I will check in the code into our repository and paste the link of the code into the description. I hope you enjoyed this video. Thank you.